Morning, everyone. Welcome to this GIS Day session. My name is Robert Gottlieb. I'm with the Indiana Department of Health. At this point in the event, you have probably been on other presentations and are used to how this works now, but if you have questions during the presentation, um, you are muted. You won't be able to say them out loud. You'll have to type them into the chat, which I will be monitoring during the presentation. Our speaker is willing to take presentation or take questions uh, in the middle of the presentation. So I'll be monitoring and chiming in if there are questions during the presentation, or we can take them at the end as well, but we'll take them in the middle as we have them. So our presentation for this session is titled Collecting Geodata via Application Programming Interfaces, API for Location-Based Applications Using Python. It's presented by Sam Strobel. He is a data analyst for the Indiana State Department of Agriculture in the Division of Soil and Water Conservation. He previously worked for the state of Indiana as environmental project manager for the Indiana State Department of Environmental Management. He has completed a BS in environmental science from the Ohio State University and master's degree in GIS from Kent State University. Sam's professional interests include using data and GIS to answer questions about the environment and conservation. I will turn it over to him.
Hi, thanks. Like was said in the introduction, this presentation is entitled Collecting Geodata via Application Programming Interfaces, or APIs, for location-based applications using Python, which is a bit of a mouthful, but this presentation is geared towards someone with a basic knowledge of the Python programming language. But if you don't have any knowledge of the Python programming language, that's okay as well. This will just kind of show you some capabilities and maybe get you interested in learning some more. So the first thing I'm going to do is give you some background on APIs. So APIs are application programming interfaces. What does that mean? You can think of it in contrast to a user interface. A user interface is how people interact with computers. So if you're working in ArcMap, ArcMap is the user interface. And a API works as a software-to-software connection, so there is no user interface. Practically, this often involves software-to-software connections over the internet, which are sometimes called web APIs. In a web API, your program is interfacing with a web server. There are a subset of APIs that are called GIS APIs, and that just means that they are have some functionality of a traditional desktop GIS software. So you might ask yourself, why would I want to use a GIS API versus a standalone GIS desktop software that I'm probably familiar with? And there are a few reasons. GIS APIs can be used across platforms, systems, and devices. They don't require an install of a local GIS or knowledge of how to use the GIS. And you don't need to store your spatial data locally. And sometimes they can be used in the automation of tasks. So there's essentially two types of GIS APIs. The first is kind of a backend for some of the desktop GISs that you may be familiar with. Like the ArcGIS API for Python, or the ArcGIS API for JavaScript. QGIS, which is an open source GIS, has an API, and Geopandas, which is a Python-specific module that doesn't have a front end like ArcGIS does. So it's exclusively run as a software-to-software connection. So the second type of API is APIs for accessing web services. Many websites host GIS data, and some of those can be accessed via API. So some examples are federal government data sources often have APIs, Indiana Map, and ArcGIS has its own API process for accessing data that's hosted online called the ArcGIS REST API. So the examples I'm going to show you today are from a workflow I made for a model called the denitrification decomposition model. So this is a process-based model for estimating carbon and nitrogen biogeochemistry of agricultural soils. It's run at the field scale. And this is something that we at ISDA use to model some of the agricultural practices that we help implement, like cover crop or no-till agriculture. And we want to see what effects these practices might have on soils. And we want to run these on a large number of agricultural practices that we implement. So here just kind of shows all of the information you need to put into this model to get your outputs get your inputs to put into the model. So most of this is geodata. It's stuff that's location dependent, like soil, what type of crop is grown, weather, etc. You could get all these processes by using a desktop API and querying spatial data sets, but I wanted to make kind of a lightweight standalone script that could create the inputs for the model on its own without the need to do a lot of geoprocessing. So the entire workflow is pretty long, so I'm just going to show two examples of using web APIs to get pieces of data that go into this model. So that's kind of the end of the background section. And next, we're going to show some code, which is hopefully going to be the interesting part of this presentation for most of you. The first thing we're going to show is how to do an API call, which is the kind of technical term for submitting a request to an API and retrieving data from it. And that's going to use the National Agricultural Statistics Service Cropscape data layer, which is an online data layer that's hosted by USDA. It's a web service that hosts remote sensing data that classifies agricultural land by crop type. And part of the web service is a GET request service to access the data. So I'm going to show some Python codes that allows you to query the web server to access the data. So the first step we have to do is import libraries. So if you're familiar with Python, this is kind of the common first step. So we just ran the import requests library, and requests is a library that makes sending HTTP requests and getting responses much easier. So web services that have an API for accessing their service will almost always have documentation on how to use the API service. In the case of the NAS Cropscape data layer, there's a section called the Developer's Guide that has the documentation on how to perform various requests. For this example, we're going to use the GET request option to get Cropscape data layer values, which is just the estimated land cover type for a given pixel. So you can see the URL in the first part of that code box. And then you can see the parameters that it needs, which you can see in the URL as well. You need the year and then just the X and Y coordinates. I'm going to run this code, and that's just going to store that base URL as a variable. And next, we are going to give some example XY data. So these are just kind of random XY coordinates. And something you need to look out for, like when using a GIS, you have to be in the correct coordinate system. Luckily, there is a library in Python that allows you to easily convert your coordinate system. And the coordinate system you're going to need will likely be outlined in the documentation. So we have our input and our output coordinate system for these 2 points, and we're just going to convert them to what we need for the request. And then kind of using the same scheme as I showed above, we're going to store our query information in a dictionary. So our X and our Y data and our year. And then we're going to send a request, which is really easy. You just use request.get your base URL and then the dictionary from above. And we're going to get the request back from the web server and just store it as a variable called REQ. So we can look at that, and you see that it's just a doesn't really show us anything because it's just a type that's specific to that library. So we can see that, and you can see it's just that type. So we need to do something with it so we can use it within our script. So we're going to turn it into a Python type string. So you do that and you see what we've gotten out from it. So this kind of looks like gobbledygook, but if you look through it, you can see that we have category corn. So that's the crop type for that point that we fed it. And then we can just use some Python string manipulation techniques to store just that information as a variable. So we do that and we get corn. All right, for our second example, we're going to use Indiana Maps API. Most of you are probably familiar with Indiana Map. It's a service that's specific to Indiana that hosts a lot of data that probably you folks help create and maintain. So we're going to use a different library in this case. We're going to use the URL lib library, and we're also going to use the JSON library because we're going to be getting our response back as a JSON. So again, in the documentation for Indiana Map, you'll be able to find the URLs and parameters to perform different queries. So for this example, we're just going to query the county layer within there to figure out what county a specific point is in. And again, we'll have to work with our coordinate system to make sure we're in the correct coordinate system for our request. You can see the parameters that we need to give for this are a little more complicated. So this is probably the most difficult part about setting up a request is setting up the parameters that you want. But if you're using it in workflow that you're going to use more than once, you obviously just have to do this once and it will be the same. So we're going to give it our XY, the field name, which would be from the table within the map. So we're just getting the uppercase name of the county and the format that we're going to get it out as a GeoJSON. So we're going to encode our parameters. Sorry, And you can see what the encoded parameters looks like. So this is pretty complicated, but that encode parameters function from our URL lib library made it really easy to just turn that dictionary that we had before into the correct output to send our request. Our encoded parameters and the county URL, and then this function to send out a request and get a response. So you can see again, the response isn't really usable yet. It's just specific to that library. But we can use the read function, and then that'll turn it into something we can use. Right now, it's in the Python type bytes, which isn't super helpful to us. So we're going to use the JSON library to turn it into Python objects. So we do that, and you can see now it's kind of a series of dictionaries and lists, and that is something that we can use. So this is kind of the pre-set up query that turns that series of dictionaries and lists and gets just the name of the county. So we run that, and now we'll have just the county name, and I'll kind of show you as we go down how you get that. So if you look at just features, and then the first set of features, properties within features, and then you get your county name. So that's just kind of how you would figure out how to get your county name from that kind of JSON objects that was converted into Python types. So now we're going to put both of these requests together and kind of turn it into a usable workflow to get data for a few different points all at once. So we're going to use the Geopandas library, which is something I mentioned before. It's kind of like a Python version of GIS that runs within Python. So it has a lot of the functionality of something like ArcGIS, not all of it, but some of it, and you can use it within. And if you're familiar with pandas, it kind of works as like tables, so it's kind of easy to work with like that. So we imported those libraries, and now we're just going to set up a pandas data frame with some kind of dummy XY coordinates. So we do that, and we have our data frame with XY coordinates. And now we're going to turn that into a geodata frame. So we're going to turn it into that is able to use those coordinates as geodata. And when working with Geopandas, you have to be sure to set your coordinates. And now I'm just going to run this, and it'll show us where our points are. And that top part is just importing a shapefile that shows the county boundaries. But those blue dots are our dummy points. And if we look at the geodata frame now, because it's in Geopandas, we have a geometry column, which is the geometry of the points. So we're going to take that land cover lookup API query that we did before, and we're just going to write it all as a function, as opposed to like individual blocks of code. So it's going to do everything that I showed before. Query that NAS Cropscape data layer for an XY coordinate for the 2020 data, and it's going to just return the NAS category as a variable. And we're going to do the same thing for our county lookup. We're going to define this as a function and return just the county as the variable. So now we can use a kind of pandas technique, which is lambda and apply, which lets us apply functions using the rows as inputs to our functions, and then write the output to a row within our table. So we'll do that, and it'll just take a few seconds for each of those functions. Now when we run our, when we look at our data frame again, you can see that for each of these points, we have the estimated agricultural cover type under that NAS cover column, and then the county that the point's within under that county column.
Hey, Sam, we've got a question in the chat from Ben Bond. It says, what was the reason for using URL-lib in the second function or script as opposed to requests?
I just wanted to show two different libraries that you can use. They both have really similar functionality. So you could use either for either of these examples. There might be some scenarios where one's better than the other. I'm not really sure what they are. It was just to kind of show you different options.
He says, good idea. Let's click here at your question slide. So was that it?
Yep, that's it.
Okay. People have other questions. Now's the time to put them in the chat. Okay, got one from Cameron. Okay, they're coming in now. This is a comment about the same question. It says URL is a Python built-in, so if you're in an environment where you're unable to install requests, it might be useful. And Susan Carter asks, is Python the best language for using an API or just your preference?
That's probably pretty subjective, but Python has the advantage of kind of being the language that most GIS users know because of the ArcPy module. And it's also pretty quick for scripting, just because of a lot of like the functionality of it. And then you have all these libraries that people can build, like the requests and Geopandas and stuff. So I would say it's probably a really good one. I don't know if it's the best though.
Yeah, I think it's generally most popular. It adds a lot of other functionality. You know, R is an option as well, but some of the functionality of Python goes beyond that. I mean, they have different purposes. People find what they need for different uses, but I think Python's kind of has the most versatility. And it's used by a lot of other people. So if you're trying to work with others, there's flexibility there as well. Not seeing any other questions. Keep it open for a couple more minutes, but we've got plenty of time. Here we go. Here's one. Or this is a comment. Philip Bernard says Java also has a lot of geospatial libraries, but I've always found Python to be much easier to work with. That's a good point as well. Python is generally regarded as a relatively easy language to use. One question I had that was more broad. You mentioned ArcPy briefly, but didn't mention it like as an API. So something I'm not as familiar with is like the definition of API, like what makes an API an API, I guess, or what makes Geopandas an API that you talked about, but ArcPy not one, for example.
That might be a philosophical question. I'm not 100% sure. I think it probably kind of is an API, but because it has to be like locally installed with you know, with the web or the standalone application on your machine. I don't know if it's considered one, but yeah, I don't know. I mean, it definitely functions a lot like an API. Like the ArcGIS API for Python really functions pretty similarly to ArcPy with maybe less functionality than ArcPy and more in kind of the HUL side of things.
Yeah, I guess when I think about it, I think about like what does what I need to rather like, is this an API? Do I need to use an API? Think about that as much.
And I think a lot of people, when they say API, they really mean like the web API side of
Mm,
things, sending requests to web servers and getting responses back. That's probably the most common way
yeah,
people use the term.
yeah, makes sense. Got a comment from Diane Osborne, says good presentation, thank you. You mentioned this at the beginning, just that, you know, you working this way makes things easy for you, simple. I mean, you're able to run a lot of code in a presentation, from your browser, just doing this. You kind of like, I guess, contextualize a bit more like a particular project that really got done more quickly or in an easier way than you know doing it in a different way, like a particular project you have in mind. I guess like some output you can point to.
Yeah, so the DNDC project, really, it's a pretty complicated um, project that would be really pretty hard to do with a just using like a standalone GIS, especially because of like the climate section of it, where we're um, doing a lot of kind of manipulation of the data. So being able to like kind of quickly grab your data and pull it out, as opposed to having to have like a whole separate um, step of kind of doing like raster geoprocessing,
Mhm.
really is pretty nice. Especially because raster geoprocessing, if you're geoprocessing an entire raster, takes a long time, whereas if you just get a value and geoprocess it in Python, it's like nearly instantaneous. So that's one good thing you can do. Another thing is like we don't have a lot of our users don't have GIS, so like being able to like kind of build things that they can use, that can query stuff using these APIs is really helpful. So we have a thing called the Region 5 model, which is kind of similar. And we actually have built some of these like API calls into Survey 123 to
Mm.
collect data, and have it kind of all in situ, and be able to do these calculations without any of our users having to do it.
Okay, that's good to know. It's interesting. I mean, yeah, we have, at the health department, we have for integrating GIS or geoprocessing or spatial analysis more into our informatics program, and we have a lot of other users that are like, interested in GIS or map making or some spatial data awareness that don't have desktop licenses. So point them to ArcGIS Online for sure. I lead trainings for that, but thinking of more flexible ways to look at spatial data is useful. I mean, some of that gets into Tableau for like simple maps, but thinking of ways to be more flexible is useful for us. Um, have your abstractions reminder on that denitrification decomposition model. It's a model process based for estimating carbon and nitrogen biogeochemistry in agricultural soils. So yeah, it takes a variety of spatially dependent inputs, which can be obtained from publicly hosted online data. So I can definitely see when you mentioned that that data can be detailed in rasters, like you mentioned, how you can imagine how processing that could be um, complicated and time consuming without this process.
Yeah. Yeah, it definitely made it a little easier on me. So that was kind of my goal. So something like this is more of something that just I use, but these definitely can be used for kind of like distributed solutions where
Mhm.
someone really just doesn't even see the back end. It just like they just get the data and
Right.
they're good to go.
I think you reminded me of a last question I had. Like, is this code shared somewhere, like GitHub or something like that, or just something you've worked on internally?
Um, yeah, I could share it to a GitHub if there's interest in that. I think most of these kind of examples would be well covered by those libraries documentation page in
Mhm.
GitHub. That would be a
Yeah.
good place to start.
Yeah. That makes sense.
Um, But if anyone wants to, feel free to reach out to me. I'm not an expert in this by any means, but I could probably get you going if there's an interest there.
Yeah, I'm definitely not trying to pressure you to do that. It was just something that made me think of like, hey, this is interesting. I wonder if it's, out there shared already or not. Just something I was curious about. Okay. It's 10:30. Could open for another minute in case there are any uh, other questions. If not, we'll wrap up early. Cameron's offering assistance. If anyone needs Python assistance, I'm usually available. Cameron at binkhatbeard.com. Thank you for that, Cameron. Yeah, I think that was something that came up one of the sessions yesterday about the food distribution map that FSSA and IoT worked on. Is we are a community of GIS users, and we have a lot of capacity to help each other and collaborate. Okay, I don't see any other questions, so I believe we can wrap up early. Thank you, Sam, for your presentation. The next sessions start at 11. So we've got some extra time. Or probably there's another session going on right now as well that we should be wrapping up. So yeah, thank you everyone for attending, and I hope you enjoy the rest of GIS Day.
Thank you.